Okay, in this video, we're going to be looking at how you can use the Jordan form in controllability and observability calculations. In previous videos, we've already seen how you can take any system. So let's say we're starting with a system that is just some state x dot equals ax plus bu. And just to be clear, we can also talk about discrete systems that are in the form x at sample k plus 1 is equals ax plus bu. So we're talking about continuous time systems where the states lead to time evolutions of the states, or discrete systems where it's a state update. What we're going to talk about today, everything completely is the same for both of these systems. So we've already seen how for both of these systems you can use these kind of brute force numerical approaches to look at controllability and observability. So for example, you form a controllability matrix, which is equal to, you just stack the B matrix and then AB as sort of the next set of columns, and you do that all the way up to a to the n minus 1 power, where n is the dimension of A. So A is an n by n matrix, and you have n states. So you're looking for this controllability matrix to be full rank. And then there's sort of an equivalent observability matrix with A and C's that are formed. And it's a numerical tool. You look at the rank of this matrix, and if it's full rank, then your system's controllable, and if it's not full rank, it's not controllable. But it's very binary in that way. Like you get a yes or no answer about controllability without really much intuition about what's going on inside. Now, we've also learned about the Jordan form of equations and how important the Jordan form is. So for example, back to our continuous time system, we know we can do this equivalence transformation. So we would switch x to some different state, let's call it x tilde, and we'd have this new A matrix that is a Jordan matrix with this new state, and then we'd have a resulting new B matrix. And there'd be a new C matrix as well, and the D matrix always stays the same. But so we know we can do a transformation to convert our system into this equivalent system in which the A matrix is now a Jordan matrix. And we've already seen how that really reveals the underlying dynamical structure of the system better than any other form that we have. And it turns out that controllability and observability is also very straightforward if you convert your system into this Jordan form. It ends up being a very clean way to think about controllability and observability. So to start, let's just look at a simple 2x2 system I've done this equivalence transformation. I'm in Jordan form. I'm going to keep working in continuous time, but the results are the exact same in discrete time. So let's think of a 2x2 system that looks like this. So I have x1 dot and x2 dot equals a Jordan matrix, and I'm just going to write a Jordan matrix. A Jordan matrix is an eigenvalue and an eigenvalue, and a 1 and a 0, and I'm not going to even care what that eigenvalue is right now. It's sort of irrelevant, times state 1 and state 2. And then I'm going to give a completely generic B matrix. I'm going to assume I only have one input. So I have B1 here and I have B2 here. So this is just a generic B matrix. And then I'm going to solve this controllability matrix explicitly. Okay, so first we're going to basically say the controllability matrix is B and AB, since I have to go up to the n minus 1 power. So I'm going to have to compute AB. So let's just compute that really quickly. So if I say AB is equal to lambda 1, lambda 0, B is B1, B2, that equals, so I have lambda times B1 plus B2, and then down here I just have lambda times B2. And so now if I pack that into this controllability matrix, I will have my original B, B1, and B2. Oh, there shouldn't be anything there. And then the next column is this one I just computed, lambda times B1 plus B2 and lambda B2. So now let's look at what happens if, for example, B1 is equal to 0. Okay, let's say B1 is equal to 0. Then what that does to my controllability matrix is this becomes 0, B2, B2, and lambda B2. And this has such a simple structure that you can see that this controllability matrix is full rank as long as B2 is anything but 0, because the first column and the second column will be different from each other, linearly independent of each other. So there's no problem with B1 being 0 in terms of my system's controllability. My system will be controllable even if B1 is 0. But if let's go back to the full controllability matrix, and let's say, what if B2 is equal to 0? See what happens. The controllability matrix will equal B1, 0, lambda B1, and 0. And so we can see that our second column is just a multiple of our first column. It's the first column multiplied by lambda. So this system is not controllable no matter what value that B1 takes on. So if B2 is equal to 0, this system is not controllable. So let's go back up to our Jordan form and look at the structure of it and see physically what that means. If we think about our ability to control state 1 and state 2, we're really talking about our ability to sort of control its evolution. So we're talking about our ability to influence x1 dot and x2 dot. If we can push x1 in a direction that we like, that means we have control over it. If we can push x2 in a direction we like, we have control over it. So if you look at the structure of this matrix, because of this 0 here, you realize that x1 has no influence over the evolution of x2. So x1 can't affect x2 dot. So the only way we have any control over state 2 is directly through the input. And that can only happen if this B2 is something besides 0. So the only way we can influence state 2 is through this input. That's not the case with state 1, because yes, if B1 was some non-zero number, then you could influence state 1. But if you look at this 1 here, you see that state 2 can also influence state 1 indirectly. So if we have the ability to push state 2 around, then we have some way to push state 1 around also in a sort of indirect way. And so this is what this controllability is revealing to us. So the straight numerical result, the straight controllability, tells us, we're looking at two explicit cases of B1 equals 0, B2 equals 0, but it's really telling us something about this structure of the Jordan form. Now, I've drawn a 2 by 2 Jordan matrix here, and it turned out that B2 was the critical entry in B that couldn't be 0. But it turns out in general, like if I were to look at a 3 by 3 Jordan matrix or a 4 by 4, the way you generalize is it's always the last entry. So it's always the bottom row of the system. So if this were a 3 by 3 matrix, it would be state 3 that you would be very difficult to control, and you'd need to make sure that B3 was non-zero. So that's how you think about that generalizing. So let's do a numerical example in which we can see how this plays out. So let me clear my board. Okay, so I'm going to stay in continuous time, but it's the exact same in discrete time, so don't let that stifle you. So let's make a big system here where we can sort of see all of the kind of ways this can go down. So I'm going to write a big Jordan matrix. So in my first block, I'm going to put -5, 1, -5, 0. So I just drew a 2 by 2 Jordan block with an eigenvalue of -5. And then I'm going to say my system has another one of those blocks. -5, 1, -5, 0. Now let's consider a different eigenvalue. So let's say like -2. So I have -2, 1, -2, and 0. And then let's consider another Jordan block of -2, but let's have it be a 1 by 1 Jordan block, so you can see that the size of the Jordan block isn't really that complicated. So this is our big A matrix, which is in Jordan form. and everything else is all zeros. So our Jordan form matrix has lots of Jordan blocks on the diagonal. In this case, we have two distinct Jordan blocks associated with -5, which also means we have two eigenvectors associated with the eigenvalue at -5. And we have two Jordan blocks associated with -2. They're different sizes, but they're still two Jordan blocks, which means there's still two Jordan matrices. And this is going to equal multiplied by x, and then I'm going to have to add b and u. And I'm going to just generically write B as this kind of big empty matrix that is kind of a tall, thin matrix. And I don't know how many inputs I have yet, so let's leave that kind of generic. Now, if you think about the structure of this matrix, and you think about what we learned on the previous slide, what we come to realize is we need to be able to control the bottom row of each Jordan block. So I'm going to draw a line over here. And there is a row associated with this B matrix right here. And it's important that that row isn't 0. Now, the question in terms of if there's multiple columns is what is the equivalent of 0 in this case? And we'll talk about that in just a second. But basically, you know that this row has to have something, because we need to be able to control this Jordan block, and we saw that the only way we can control this Jordan block is for the input to have direct control over this last entry in that Jordan block. That's true here as well. So I need this row to have stuff in it. It can't be just zeros. But if you think about the dynamics of this, you've got two parts of your system. So this part of your system is describing state 1 and state 2, and this part of your system is describing state 3 and state 4 in this equivalently transformed state equation. But they both have identical dynamics. They both have this eigenvalue at -5, which is equivalent to a time constant of 1/5 seconds. So it's important, if I want to completely control this state to wherever I want, oh, I'm sorry that I put a little dot there, that shouldn't be there. If you want to be able to control these states and these states independently of each other, even though they have the same natural dynamics, it's important that this row of B and this row of B are not only not 0, but they have to be different from each other, so that you can have U affect these two states and these two states different from each other, since they have the same natural dynamics. So it's important actually that beyond those two just being not 0, it's actually important that we need these to both be linearly independent from each other. So these must be linearly independent. And when I say they must be linearly independent, what I mean is if you want your system to be controllable, they must be linearly independent. This is kind of interesting right here, because already we see that for this to be true, we know we have to have at least two inputs, because the only way these two rows could be independent from each other is if they're at least 2 across, 2 wide. So we already see that we have to have two inputs for this system for it to be controllable. That's like a minimum condition. If we go down to the -2 eigenvalues, the same basic rules apply. So I know the bottom row of this Jordan block has to be non-zero, and I know the bottom row of this Jordan block. In this case, it's a 1x1 Jordan block, but that's still the bottom row of it. Those two bottom rows have to be non-zero so that you have control over those states. But just as with the -5, these two states have the same natural dynamics, the same time constant with this -2 eigenvalue. So it's important that these two rows are linearly independent from each other. So let's just write that. Must be linearly independent for this system to be controllable. Now, what isn't important is that these rows are linearly independent from these rows, because basically these states down here already have a completely different time response than these states. So that fact alone is enough for our inputs to push them around differently from each other. So the test you do is you look at all the Jordan blocks for which they have the same eigenvalue, and you make sure the rows of B that are associated with the last row of those Jordan blocks are all linearly independent. Then you do that for each individual eigenvalue in the system. You make sure for all the Jordan blocks, including if there were only one Jordan block, you make sure those rows are linearly independent. In the case of only one Jordan block, if let's say we only had this, what it would mean to say this row has to be linearly independent when it's the only row means it just has to be a non-zero row. So this has all been about controllability, but the interesting thing here is we haven't actually done any, weird kind of numerical test. We've just looked at the Jordan form and we can see if it is or isn't controllable. Now, what if the answer was this wasn't controllable? If we found that, for example, these two rows weren't linearly independent. What that would mean is you would have to make them linearly independent. And if we assume we can't change the system we already have, so these numbers that are in these rows are set, the way we would make them linearly independent is we would add another input. And we'd have to add an input in the right place. And by adding another input here to U, what we would do is we'd add another column to the B matrix, and you'd want the number that gets added here to be different than the number that gets added here in a way that now these two rows are linearly independent. So effectively, we'd be adding a new actuator to our system that affects these states differently than it affects these states. And that's the way we get to controllability. So unlike the other tests for controllability where it's a very yes or no answer, it is or isn't controllable, this test in Jordan form actually lets you look at how you would fix your system if it's not controllable, or at least give you ideas of how you might fix it. Now, so far we've only been talking about controllability, but the same basic kind of idea about knowledge and things we can and can't know from our system applies to observability in the Jordan form too. So if we were to think of, for example, have a set of outputs, and our C matrix, similarly to our B matrix, let's just write it like some generic C matrix, times X. And then there's going to be this DU matrix that's just not important at all. What we're going to find, just like here where it was important that the last row of each Jordan block had to be linearly independent, here it's going to be important that the first column of each Jordan block is linearly independent. So I go down the first column of this Jordan block and the first column of this Jordan block, and I consider those columns of the C matrix. And those two columns must be linearly independent. Now it must be linearly independent for our system to be observable. And then we look at the first columns of our C matrix, and those columns live here, and those have a different dynamic response, but they have the same dynamic response as each other, and those two columns must be linearly independent for our system to be observable. So, excuse me. So now let's say that this test failed and you said, oh, these two columns aren't linearly independent. What that would mean effectively is that you need to go back and add a new sensor. And so as you add a new sensor, you'd be adding a new row to your C matrix, and you'd want to add a sensor such that the number that appears in this position and this position are distinct from each other. So that new sensor lets you see these states differently than it sees these states. And so, so now we have sort of the final tool we're going to learn for controllability and observability that, in my opinion, is the single best tool for controllability and observability, because we're already capitalizing on the Jordan form so much. It's such an important way to look at our system because it so clearly represents sort of the states that are coupled and not coupled with each other and the underlying dynamic response of our system because we can see the eigenvalues explicitly. So we're going to use that same Jordan form not only to look at dynamic response, not only to look at stability, but also to look at controllability and observability in a very intuitive way that for an engineer lets you actually think how to fix your system and make it controllable or observable when it's not.